record show, my class trying to get me to slack off. They didn't even ask me a question. It was like,
I know.
no class Tuesday. Like, and they're like, yes or no, Jhevon. Like, it's not really a question.
I wrote the question mark originally.
Don't erase the board, Jhevon.
He said no. He said no. No class?
I cannot believe this. But I've important stuff to do with Markov chains. Let's do this game.
Boy.
Wait, so it's
I don't even know how to spell Markov.
So this time, aren't we already having that Wednesday off? You guys want the Wednesday and Tuesday?
It's just like Wednesday.
So we can start the week off good.
We have families.
So
Okay,
so last time we had a Markov chain that looks like in fact was this Markov chain. I typed it up, problem 1. There are 2 other problems typed up. We're gonna look at those. We'll see how you guys do, see if I feel like canceling class on Tuesday.
Aww.
Take your time, Sean. Take it slow.
I'll Venmo you $5.
Okay. I live here.
Pass those here? Oh, never mind. Can you pass those this way? Yeah, pass them.
Okay,
Oh, never
so
mind.
there was a machine. It was if it's working, there is a 90% chance that it will continue working. There's of course a 10% chance that it will move to a state of not working. If it's not working, there was an 80% chance that they'll fix it and it'll be working by the next day, and there was actually a 20% chance that it will remain not working. So we had that Markov chain last time. And I think 3 steps was too much to actually figure out what was going on. Let's do a 2-step process so you can kind of see what I was talking about. So let's say we're in state 1. Probability we will be in state 1 again after 2 time steps. And so pretty much if we're starting at 1, we can move to some other state, but I ultimately want to move back to 1. And it turns out there are only 2 states, so it turns out there are only 2 possibilities for this. We can always stay in state 1, so we can just loop around and continue to work twice, or we can move to a state of not working and then move back to a state of working. So those are the only 2 ways you can go from 1 to 1 with 2 steps. And so we can either stay here for both steps, or we can jump over here and then jump back. That's a way that we can go from 1 to 1. And we know that if we're in state 1, what is the probability that we move to state 1? Well, that was 0.9. And if we're there, what's the probability that we move to state 1? That was 0.9. Or, because these are mutually exclusive events, if we're in state 1, what's the probability that we move to state 2? Well, that was 0.1. And if we're in state 2, what is the probability that we move to state 1? That was 0.8. And Bayes' theorem kind of tells us that actually makes sense for what is the probability that we remain in state 1 after 2 days. But I also wanted you to look at this. Consider p squared. Now you might have recalled p was the matrix 0.9, 0.1, 0.8, 0.2. And if I square that, this is going to be important. What is p squared going to be? Now I want you to realize that it is not just the square of each component. Matrices aren't that easy to actually square. If you multiply them together. So, I mean, we're not in the class where I'm going to teach you how to take powers of matrices efficiently, but there are ways using things called eigenvalues and eigenvectors. I'll mention them, but we won't really actually do that. Now, if we were to actually multiply these two, in the first position, this is 0.9 times 0.9 plus 0.1 times 0.8. In the second position, that is 0.9 times 0.1 plus 0.1 times 0.2. In this position, that is 0.8 times 0.9 plus 0.2 times 0.8. And this would be 0.8 times 0.1 plus 0.2 times 0.2. And I want you to notice the 1, 1 position, specifically in regards to this question. And you realize it's actually exactly the same expression. So, in other words, what I'm trying to show you with that example where 3 steps was too big because then I'd have to cube a matrix. I'm not going to do that right here. What you realize is if you want to know what's the probability of moving to one position to another position in a certain number of steps, what that requires you doing is just raising the transition matrix to that number of steps and look in the position that gives you the starting and end points that you want. So the row is going to tell you your starting point, the column is going to tell you your ending point. So I could have asked the same question. What is the probability that if I'm currently in state 1, I will move to state 2 within 2 number of steps? Well, that would mean I would look in 1, 2. That's going to be the probability. That if I'm in state 1, I would be in state 2 after 2 time steps. This would be the probability that if I'm in state 2, I will be in state 1 after 2 time steps. This is the probability that I will be, if I'm in state 2, I will remain in state 2 after 2 time steps. And so that answers one of the first questions of how we can actually predict being in a certain position in a certain number of steps. This answers, I believe I called it question 1 last time. What is the probability? That xn will equal some particular value I after n steps. Right? So if I were to ask the question, okay, I know the machine is working today, what about 62 days from now? If I happen to show up 62 days from now, what is the probability that the machine is going to still be working? What I would do is I would take this matrix, raise it to the 62nd power, of course I'd use a computer to do this, and I would look in the position 1, 1. That is going to tell me the probability that I'm going to be in that state in 62 days from now. And this is one of the main applications of Markov chains, in fact, and it can get really crazy and really big. You will have matrices that are millions by millions row. You can have like a 1 million by a 1 million matrix, and they're like, okay, we're currently in position 5. What is the probability that we're going to be in position 10,000 if we were to randomly just travel around this chain in 20,000 steps? What you're going to teach a computer to do, not directly, there are going to be shortcuts to doing this, is so, okay, you're going to take that 1 million by 1 million matrix, you're going to raise it to the 20,000th power, you're going to look in position 5, 10,000. That's the probability that you're going to end up with. So that answers that question. To figure out what's going on in n number of steps, what we can expect to be happening, it's a matter of raising the transition matrix to a certain probability, to a certain number, because it just so happens to turn out matrix multiplication happens to behave like Bayes' rule in a very serendipitous fashion. So let's talk about the next question that we wanted to answer. I don't remember if I put this as question 2 or question 3, but let's rename it question 2. What is the long-term behavior? So I don't really have a specified time in the future when I'm going to show up and check whether this machine is working. So make it an unspecified time in the future. In the long run, in the long term, if I were to just show up at a random day at some point far off into the future, what is the chances that this machine will be working when I'm looking at it? So, how would we actually do that? Well, so recall we also found something called the initial state matrix. This was S1. That pretty much tells you the probability of being in a certain state in the beginning. So this was state 1, which means we were working. Or we could be in state 2, not working. And we know that upon installation, there's a 99% chance that this thing is going to be working, and there's a 1% chance that it is not going to be working. And so now we might ask the question, well, okay, given that this is our initial state, what is the probability that we're going to be working tomorrow, right? So let's pretend I know the stats about this machine. I know that one was installed today. I don't know if it's working or not. If I were to bet, if I show up tomorrow, is it going to be working? What would I bet? Or how confident would I be? Well, the transition matrix, as you can see, it kind of tells you how things are going to happen. What you would do is you would take S1 times P. This is going to be a 1 by 2 matrix multiplied by a 2 by 2 matrix, which we know is possible. And we're going to multiply this. So this is going to be 0.99 times 0.9 plus 0.01 times 0.8. Move over to the next one. 0.99 times 0.1 plus 0.01 times 0.2. That will be the second one. Can someone calculate this? Or did we do that one already? Huh?
Yes, it's
0.899
and the other one's 0.10.
So, this is if we show up tomorrow, there's going to be an 89.9% chance that it's working. Regardless of the fact that I know it's working today or not, that would be the guess. This is what we call S2. And that is the second state matrix. So if I know what's going on initially, if I want to figure out what's going on one step later, I can just multiply by the transition. What if I wanted to find what's going on 3 days after installation? Well, I'll take that and multiply by the transition matrix. So I'll take the S2 and multiply by P. And I think I actually did some of these. I did a few of them because I wanted to see if you could pick up on a pattern. So the third state matrix was S3 was 0.88899, 0.11101. 4 days later, I would take that state and see how things transition. And 4 days later, we have 0.888899. Over here, we have 0.123401. 5 days later, I would take S4 multiplied by P. I got 0.888889. I just cut it off there. But here, 11111. So that's 0.1. S6. Take S5 times SP times P. I think that's the last one I computed. That's 0.8858. 9, and then there were 6 ones. 1, 2, 3, 4, 5, 6. And you can imagine I could have kept doing this. So, if you were to hazard a guess as to the long-term behavior of this machine that got installed today, what would you guess? If I were to show up at some far point into the future, what are the chances that it's working? What do you think it's going towards? Huh? 0.8 repeating forever. You notice that the 8s just keep stacking up and the 1s just keep stacking up. This one, you would think in the long term it goes to 0.888 forever, 0.111 forever, because that seems to be the pattern that you're seeing unfolding. So notice, I don't remember if I wrote this down, so I'm just going to write it down again. To compute Sn plus 1, what I do is I can take S1, and if I multiply by p, that gives me S2, multiply by p again, S3, and keep multiplying by p. So if I multiply the original by p n times over, that gives me the state in the next step. So that's going to be something important. That's an important equation to know. Moreover, there seems to be a pattern here. It seems like this thing is heading towards something. It seems like our S1 p to the n is going towards a particular matrix. Let me denote that S bar. Right? So some matrix. Okay, so sometimes the long-term behavior of a Markov chain behavior, state or behavior. Markov chain. Uppercase N. It's named after the guy who thought about it. Tends towards particular state matrix. If such a matrix exists, we call it a steady state matrix. So clearly, such a matrix would be very important for us to figure out if it actually exists. This allows me to predict the future far into the future, assuming that the system behaves the way that the Markov chain is assumed to behave. And we denote it S bar if it happens. Now, I'll tell you right up front, not all Markov chains have a stationary matrix, but this one seems to tell me that it is heading towards something. So, here's the thing. How would I know that such a matrix exists? If all the state matrices, so we have, basically what's going on is all the S sub n's, they're moving towards this guy over here. How would we find S bar if it exists? Any ideas? So if I keep multiplying by p, all these matrices are getting closer to some other matrix. How would I figure out who that matrix is? How would I know for sure that in this case it's 0.888 repeating? How do I know for sure, not just guess? Yeah?
Is the matrix that they'll tend towards S2? Because it seems like that they're gradually increasing trying to get back to that. Or they're like, I don't know, is that the one or not?
Oh, well, let's think about that question, which is a perfectly valid question. Let's say all matrices go towards this guy, right?
Yeah.
If you actually hit that guy, meaning that you think we discovered him in S2, what would be the next thing? It would have to be the S2. It would have to repeat exactly, right? If such a matrix exists, once you get there, you're going to stay there, right? Because who is he going to head towards, right?
Yeah.
Everyone wants to be that guy, including that guy, right? He's that guy. He's not going to go anywhere. He is already what he wants to be. Everyone is going towards that, which means when you hit this guy, you're going to stay there. Given that, how do you think we can find it?
It
Yeah.
has to be some type of identity matrix, like with P, it's like you have to be able to multiply by P again to stay at S bar.
Exactly. Notice, no, it must satisfy.
Does that mean we have class canceled on Saturday?
He can have class. So
That's not
this
all.
means if you take S bar and you hit it with the transition, what's going to happen? Nothing. It is what everyone heads towards, which means he's going to head toward himself. So that's how we can figure out what this matrix is. So if I want to figure out in this situation, is there a situation that this Markov chain heads towards? Is there some sort of steady state? Something that I can assume in the long term, this is what's going to happen. What we could do is we could set, well, or we don't know. We think we know, but we don't know what it is. So what I would do is I would use variables, right? Assume that that's what it looks like, x and y. Now I'm going to find x and y. This means that xy times this guy, 0.9, 0.1, 0.8, 0.2, must be equal to xy. What does that mean? Well, that means 0.9x plus 0.8y, and then 0.1x plus 0.2y equals xy. And what does that mean? Well, we know about matrix equality. Corresponding entries must be equal. So this means that 0.9x plus 0.8y must be equal to x. And it must be that 0.1x plus 0.2y must be equal to y. Which means I can move x to that side. This would be minus 0.1x plus 0.8y equals 0. And I will also have, if I move y to that side, minus 0.8y equals 0. What do you notice about that system? Can we solve it for x and y? No, why not? They cancel each other out. They're actually the same equation, right? So I guess we can't find it. Or can we?
Oh, shucks.
He's gonna like, oh damn it, I thought class was gonna end here. I guess we can't do it. Let's get out of here. Like, no, of course not. Come on. What is the relationship between x and y? X and y is assumed to be what? A state matrix. Which means I actually know more information about x and y than I just wrote down. What else do I know about x and y? There are entries in a state matrix. Yeah?
So I mean they have to add up to 1.
They have to add up to 1. The sum of all probabilities is 1. So I automatically, at any given time, have this. Okay, so those two don't have to show up.
Oh, weird.
Wait, like actually?
So then, so this is going to always be true, right? S bar is a state matrix.
If one person don't show, one person.
This must be true by the axioms of probability. So now I have this system. So that's 1, 1, 1. I can multiply this by 10, multiply that by 10, 0. So, and 1, 1, 1. Say row 1 minus row 2, 0, this minus that. Row 1 minus row 2. It's a 1 minus a minus 8, which gives me plus 9. 1 minus 1, that's that. Then I can do
Yes, and then x plus y.
then I can do 9 row 1 minus row 2. And then I can just divide by 9.
And the second line of 0, 20,
So this would mean that my x is 8 over 9, and my y is 1 over 9. By the way, what is 8 over 9 as a decimal? It's actually 0.8 repeating. 1 over 9 is actually 0.1 repeating. So it turns out that's actually what this Markov chain will do. So if I were to say, far into the future, if I were to make a guess, is this machine going to be working if I show up 1,000 years from now and it's actually still running? Is it actually going to be in a functional state or a non-functional state? Well, there's going to be an 88% chance that I'll find it fully working. Yeah, so I can predict it far into the future. I'm going to show you some cool applications of this later on, but right now I'm kind of showing you how the theory would work. Every now and then you have a Markov chain where if you find a transition matrix and you keep hitting it with a state matrix, they will go towards something. That thing is actually telling you the probabilities of the long-term behavior. What is the probability I'll be in a certain state in the long run? Yeah.
Why did you choose to use 0.1x minus 0.8 in the matrix under 111 instead of like negative 0.1?
They're actually the same, so it wouldn't have mattered, right? So even if I had put the negative and the positive, I could have just multiplied that through by -1 or
Okay.
so it doesn't matter. I just randomly chose.
So whenever the two will cancel out, you just pick one randomly?
Yeah, because essentially they are 1.
Okay, yeah.
Right? This one is just -1 times that one. It doesn't change the equation at all.
Okay.
Yeah, so I just randomly picked one. So having those two is kind of like having one equation. So I would have one equation, 2 unknowns. I need another equation with those unknowns. Yeah.
Does it matter that you drop the decimal? Instead of like 0.1?
No, I dropped the decimal to make it easier for me to compute by hand. I'm a human being. I don't want to be here adding decimals. Okay. So, when does a thing like this happen? It turns out we know when it happens. I'm going to tell you. It's cool like that. So, definition. A Markov chain is called regular, right? So we have something called a regular Markov chain. If for its transition matrix P to the K has only positive entries for some power of K. Okay? And now here is the thing. So here's a very cool theorem that allows us to make these long-term predictions, and it's really crazy how accurate this thing can be. It's a theorem. Suppose P is the transition matrix. For a regular Markov chain. And S1 is any initial state matrix. Meaning, distribute the probabilities however you want in the beginning. Right? Oh, there's a probability of this, we're in this state, and that we're in that state, and that we're in that state. It doesn't matter, right? It doesn't matter the situation. Then, 1, there is a unique steady state matrix. S bar. That all SK will approach. And it's regardless of your initial state. Markov chains that have this property, it's such that it doesn't actually matter where you start. It doesn't matter that there was a 99% chance I was here and there was a 1% chance I was there. Even if I flipped it, even if I said, you know what, there's a 1% chance that it's working when it's installed, and there's a 99% chance it's not working. What is going to be the probability it's working in the long term? It's still going to be 88%. It's not actually going to change anything. So there's going to be a unique steady state matrix that this thing will approach. So its long-term behavior is predictable. You will notice that for our transition matrix, it was regular, because if I take k equals 1, I had only positive entries. This thing is to check this gets problematic if sometimes you set up a transition matrix and there are actually 0 probabilities in the matrix itself. And then you have to worry about, if I keep multiplying, will all the zeros disappear eventually? That's the question. And as far as I know, no one has answered that question yet. We don't really know how to predict when or if all the zeros will disappear, but you just kind of know it when it happens, because you can just look, oh, there are no zeros anymore. But in the event that we have a transition matrix with only positive entries, there will be such a steady state matrix. We will be able to find a guy. 2. The long-term transition will also approach something. There will be a steady state transition matrix. In fact, I even know what it's going to look like. P bar will be equal to a matrix the same size as P with all rows equal to the S bar. So, for example, above, basically what I'm saying is that if I were to take our particular transition matrix, raise it to k power, and keep multiplying forever and ever, higher powers and higher powers and higher powers, this matrix will get closer and closer and closer towards the matrix 8 over 9, 1 over 9, 8 over 9, 1 over 9. It'll repeat the steady state matrix in each row. So if I were to take the transition matrix 0.9, 0.1, 0.8, 0.2, and keep multiplying it by itself, and just keep going, eventually things are going to head into this direction. So that's how you can talk about long-term behavior. We've answered the question on long-term behavior. And it turns out, if a matrix is not regular, then this might not happen. But if it is regular, we know this happens. The steady state matrix is worth looking for. And so that's really nice. Whenever we have a situation where we realize, hey, we can describe this as a Markov chain, and hey, the Markov chain is regular, it gives us a lot of predictive power. We can do a lot of really cool things with that, and I will mention some of those next. But theoretically, is that all I wanted to talk about? I think so. So what I want you guys to do now is I'll give you guys 5 minutes to attack problem 3. So an insurance company found that on average over a period of 10 years, 23% of drivers in a certain zip code who had an accident 1 year also had an accident the following year. Only 11% of those who did not involved in an accident had an accident the following year. Using these as probabilities, draw the transition diagram and find the transition matrix. So do A and B, And then we'll do part C together. I'm sure you know how to set one of these guys up.
Yeah, you used this one. I didn't pay attention to that because I was just trying to do it the other way. Maybe it looked like a weird Please get
Let's look at this. Insurance company on average over a period of 10 years, 23% of people who have an accident in 1 year is going to have an accident the following year. So I think the focus is on accidents, so those would be my two states, I guess. Say one has an accident in the year, two, no accident in the year. can either be in a state of 1, one of those people who didn't have an accident, or I can be in a state of 2, had an accident. Okay, so 23% of drivers who had an accident 1 year also had an accident the following year. What does that mean? What does that tell me?
They stay at 1.
They stay at 1. So if I had an accident, there's a 23% chance that I will have an accident the following year. Okay. Only 11% of people who did not have an accident had one the following year. So if I'm in a position of not having an accident, what are the chances that I will get into an accident?
11%.
It's 11%. Is it possible to go from 1 to 2? Yeah. What would that be?
Is it 0.89?
Yeah.
So if I'm at 1, there's a 23% chance I'll stay at 1, which means the complement is meaning I leave 1. So that's going to be 77. And if I'm at 2, there's an 11% chance that I will leave 2, which means, what's the chance that I will stay at 2? So that is the Markov chain for this diagram. Very similar to the last example, which is why I only gave you 5 minutes. What would the transition matrix look like? So basically, remember what this means. We are going to put the probability that I move from state 1 to state 1, the probability that I move from state 1 to state 2, the probability that I move from state 2 to state 1, the probability that I move from state 2 to state 2. I'm really just going to fill in these probabilities. So 1, probability that I stay at 1. You can see from the diagram there that that is going to be 0.23. 1, the probability that I'm going to move to 2, well, that's going to be 0.77. I'm at 2, the probability that I will move to 1 is 0.11. And I'm at 2, the probability that I will stay at 2 is 0.89.
It always adds up to 1 across
The rows must always add up to 1.
Yes, I bet.
So you need to make sure that that's going to happen. That's called stochastic matrix. There's a whole thing called stochastic processes that studies matrices like that, whose rows add up to 1. If you know that 5% of drivers had accident this year, what's the probability that a random selected driver will have an accident next year? How you actually do see? We're not going to calculate it, but tell me how you would do it. Yeah?
Just multiply S1 by P.
Right, but what is S1?
116.
5% of drivers, right?
Oh, S1.
Yeah. Multiply that by P, that gives you, and then look in position 1, that will tell you the percentage chance of having an accident. And if I do that, get that answer and multiply by P again, look in position 1, that's how many people would have an accident 2 years later. I will see you guys on Tuesday.
Except for us.
Except for those two. Finish the rest of the problems on the handout, and we'll run through them on Tuesday and do something.